Space appears empty at first glance. A dark field scattered with points of light, with long distances between everything that matters. But emptiness is often only a limitation of human senses. The farther something is, the more it hides. The larger a system becomes, the more its details fade into simplicity. In this episode, the focus is on two machines that changed how the solar system is understood, and then quietly kept going, long after their most famous moments. Their names are Voyager 1 and Voyager 2. They were launched in the late 1970s, at a time when spaceflight still carried the texture of a new era. Bold mission plans, analog hardware, and computers that would feel primitive today. And yet, these spacecraft remain among the most successful and enduring scientific instruments ever sent beyond Earth. Voyager is often described as a journey through the solar system's outer planets. That description is true, but incomplete. The flybys of Jupiter, Saturn, Uranus, and Neptune were only the beginning of the larger story. Because after the Grand Tour, Voyager continued outward into a realm that is difficult to visualize and easy to misunderstand. Beyond the orbit of the outer planets, the solar system does not end abruptly. It thins, it fades, it becomes less a place and more a transition. The sun's influence changes character. Gravity remains, of course, but the environment, the charged particles, the magnetic fields, the subtle pressure of solar wind, begins to shift towards something else. Voyager's long, quiet drift has become a kind of benchmark, a real physical object moving through the boundary between the sun's domain and the galaxy beyond. And because Voyager is still communicating, however faintly, it provides direct measurements of a place that was once only hypothetical. This is why Voyager matters now. It is not only a historical mission. It is an ongoing experiment at the edge of a system that defined human cosmology for millennia. Welcome back to Beyond Space. Where we explore the universe, one mind-blowing idea at a time. To understand what Voyager found, it helps to begin with what Voyager was built to do. The Voyager missions were designed around a rare opportunity, an alignment of the outer planets that allowed a spacecraft to visit several of them using gravity assists. A gravity assist is not a trick in the theatrical sense. It is a clean consequence of orbital mechanics. A spacecraft approaches a planet on a carefully chosen trajectory. The planet's gravity bends that path, and because the planet itself is moving around the sun, the spacecraft can gain or lose speed relative to the sun, depending on the geometry of the encounter. It is possible to think of this as borrowing a small amount of the planet's orbital energy. The planet's motion is vast, and the spacecraft is small. The planet does not notice. But for the spacecraft, the difference is enormous. This technique allows missions that would otherwise require too much fuel to become feasible. Voyager used this method to reach the outer planets with efficiency and to continue beyond them with speed that would have been impractical with propulsion alone. The famous results are well known. Voyager's close-up views of Jupiter's turbulent atmosphere, the intricate structures of Saturn's rings, the discovery of active geology, and surprising worlds among their moons. Voyager 2's later encounters with Uranus and Neptune provided the first detailed look at those distant planets, blue worlds defined by cold, wind, and faint sunlight. But the heart of this episode is not the flybys. It is what came next. After the planetary encounters, Voyager's mission shifted into what can be described as the Interstellar mission, a long-term effort to measure the outermost environment of the sun's influence and the beginning of the interstellar medium. This requires a concept that is sometimes overlooked. The sun's influence is not only gravitational. The sun is not simply a massive object holding planets in orbit. It is also a source of particles and fields that shape the space around it. The sun continuously emits a stream of charged particles called the solar wind. This wind is thin, nothing like air, but over astronomical distances it creates a measurable environment. It carries the sun's magnetic field outward, stretches it into space, and forms a bubble-like region around the solar system. This region is called the heliosphere. The heliosphere is sometimes described as the sun's protective bubble, and in a broad sense that is accurate. The solar wind helps deflect or modulate some high-energy cosmic rays from outside the solar system. It shapes how charged particles behave in the space around the planets. It defines a boundary between a region dominated by the Sun and a region dominated by the galaxy. However, the heliosphere is not static. It is influenced by solar activity, by the Sun's magnetic cycle, and by the broader interstellar environment through which the solar system moves. The heliosphere also has a structure. It is not an undefined haze. It has layers, boundaries, and transitions that can be measured, if a spacecraft can travel far enough. As Voyager moved outward, it approached the region where the solar wind slows dramatically. This slowing happens because the solar wind expands outward and gradually loses energy, while the pressure of the interstellar medium becomes more significant. At a certain point, the solar wind becomes subsonic relative to its own internal properties. This boundary is called the termination shock. The termination shock is not a shock wave like an explosion, but rather a transition in a plasma flow, a place where the solar wind changes from faster to slower, from smoother to more compressed. Beyond the termination shock lies the heliosheath, a turbulent region where solar wind particles are slowed, heated, and deflected as they encounter the external interstellar pressure. The heliosheath is sometimes described as the outer layer of the heliosphere, the region between the termination shock and the boundary where the Sun's solar wind is no longer dominant. That final boundary is called the heliopause. The heliopause is one of the most conceptually important boundaries in space science because it represents the point where the outward pressure of the solar wind is balanced by the pressure of the interstellar medium. It is the practical edge of the Sun's plasma influence. It is easy to imagine the heliopause as a neat spherical shell, but in reality it is likely asymmetric, shaped by the solar system's motion through the galaxy, by variations in interstellar density and magnetic fields, and by changes in solar activity over time. The heliopause is also invisible to human eyes. It emits no obvious glow. There is no signpost in the dark. But Voyager can detect the change. It can measure particle density, magnetic field properties, and the characteristics of plasma waves. These measurements allow scientists to infer when the spacecraft has moved from one environment to another. In 2012, Voyager 1 crossed into what is considered interstellar space by passing the heliopause. Voyager 2 followed in 2018. This is not simply a milestone for distance. It is a milestone for environment. The space beyond the heliopause is still within the Sun's gravitational influence, of course. The Sun's gravity extends indefinitely, though it weakens with distance. But the heliopause marks the edge of a region where the Sun's wind and magnetic field shape the behavior of charged particles. When Voyager crossed that boundary, it entered a region dominated more directly by the interstellar medium, the thin plasma and magnetic field that exists between stars in the Milky Way. The significance of this cannot be overstated. For the first time, a human-built instrument was directly sampling the conditions in interstellar space, not through remote observation, but through direct measurement. Voyager's instruments, by modern standards, are not numerous and not powerful in the way contemporary spacecraft can be. But they are well chosen for this environment. They can measure charged particles, magnetic fields, and plasma waves. They can detect cosmic rays. They can provide data about density and field strength that helps build a picture of the boundary region. And there is another aspect to Voyager's journey that makes it both scientifically valuable and emotionally compelling. Voyager is still communicating with Earth. Communication across such distances is not intuitive. A radio signal spreads out as it travels. Its energy is distributed over a growing sphere, becoming weaker with every passing kilometer. By the time Voyager's signal reaches Earth, it is extremely faint, far below the threshold of ordinary detection. To receive it, Earth relies on networks of large antennas and sensitive receivers. The signal is extracted from noise through careful processing. It is a faint thread connecting a small spacecraft to a planet it left decades ago. This connection also has a time delay. Commands sent from Earth take hours to reach Voyager. Voyager's response takes hours to return. Interaction is slow and deliberate. Every command must be planned. Every adjustment must be cautious. There is a calmness to this style of exploration. It is not responsive in real time. It does not involve dramatic course corrections. It is long-term stewardship of a distant machine that cannot be repaired directly. Voyager's continued operation is also limited by power. Voyager is powered by radioisotope thermoelectric generators, RTGs. These devices produce electricity by converting heat from the natural decay of radioactive material into electrical energy. RTGs are reliable for long-duration missions because they do not depend on sunlight, which becomes too weak in the outer solar system. But RTGs produce less power over time as the radioactive material decays. This creates a gradual decline in available electrical energy. Over the years, mission controllers have had to turn off instruments, heaters, and subsystems to conserve power and keep the spacecraft operating as long as possible. The process is not dramatic. It is methodical. An instrument is turned off permanently to preserve electricity for another. A heater is shut down, forcing systems to operate at colder temperatures. The spacecraft becomes simpler and quieter but still functional. This gradual fading adds an unusual dimension to Voyager's story. It is a mission that is ending slowly, not through failure, but through the physics of time and decay. The spacecraft is not dying in a sudden moment. It is being gently reduced. And yet, during this long reduction, Voyager continues to teach. It has measured the outer boundary of the Sun's influence. It has helped refine models of the heliosphere. It has provided data about interstellar particle density and magnetic fields. But Voyager also carries something that is not scientific equipment. It carries a message. The Golden Record is perhaps Voyager's most famous cultural artifact. It is a gold-plated copper disc attached to each spacecraft, designed to survive for a long time in space. It contains audio recordings, music, images, and information intended to represent Earth. It includes greetings in multiple human languages, sounds of nature, and selections of music from different cultures. It includes encoded images, diagrams, and photographs meant to convey basic information about humanity and our world. The Golden Record is sometimes presented as an attempt to communicate with extraterrestrials. That is part of the intent, but it is important to keep the context clear. The probability of an alien civilization finding Voyager is extremely low. Space is vast. The spacecraft is small. The timescales are enormous. But the Golden Record is not only a practical communication attempt, it is also a symbol of how humans choose to represent themselves when faced with the unknown. In this episode, it is useful to treat the Golden Record not as a promise of contact, but as a mirror, a human artifact placed on a spacecraft that will outlast its builders, carrying a curated snapshot of life on Earth. It says something quiet but meaningful, that in a universe that does not acknowledge us, we still chose to introduce ourselves. This brings the episode back to its central theme. Voyager is a message we sent into the dark, but the universe does not send messages back in the way humans do. It does not respond with language, it responds with phenomena. The moment Voyager crossed into interstellar space, it became part of a broader environment, one that produces signals, radiation, bursts, and patterns. Not because the universe intends communication, but because physics generates structure. In later episodes, those signals will become the focus. Radio bursts, repeating pulses, and the strange events that stand out against the background of cosmic noise. But in this episode, the focus is still on the outgoing message, the journey outward, beyond familiar worlds, into an environment where the sun's wind no longer dominates. There is also a subtle shift in perspective that Voyager encourages. For most of human history, the solar system was the universe. The sun, the planets, and the fixed stars formed the complete framework. Even after the discovery that stars are suns and galaxies are distant systems, the solar system remained our direct neighborhood. Voyager has physically crossed the boundary where the solar system stops feeling like the center of a controlled domain and begins to feel like a region inside something larger. This is not a philosophical statement, it is a measurable one. The properties of space have changed around the spacecraft. The sun's influence, in the form of solar wind pressure and heliospheric magnetic structure, has given way to interstellar conditions. It is now more accurate to say that Voyager is moving through the Milky Way's environment than through the sun's. And the Milky Way is not quiet. The interstellar medium is thin, but not empty. It contains gas, dust, cosmic rays, and magnetic fields. It is shaped by supernova, stellar winds, and the slow churn of galactic evolution. In that environment, the solar system itself is moving, traveling through the galaxy as part of the Milky Way's rotating disk. This means the heliosphere is not a perfect sphere sitting still in space. It is a structure interacting with the interstellar flow. Voyager's data helps reveal this interaction. There is also a poetic contrast worth noting, even in a neutral documentary voice. Voyager is extremely far away, but it is still connected to Earth through a faint radio signal. It is in a region where sunlight is weak, but its systems still operate because of a heat source carried from Earth. It is a machine that runs on slow decay, drifting in a place defined by long time. It also represents a style of exploration that is increasingly rare, a mission designed to last beyond a single phase, beyond a single generation of engineers, beyond the era that launched it. Voyager is not optimized for short-term content, it is optimized for endurance. In this episode, that endurance is part of the meaning. Voyager's story is not a sprint toward a single discovery. It is a long walk into a boundary region, collecting data and quietly extending the edge of what is directly measured. The question of what Voyager found can be answered in technical terms. Changes in particle density, magnetic field properties, and plasma wave measurements consistent with a transition into interstellar space. But the question can also be answered in a broader sense. Voyager found that the solar system has an edge, an environmental edge. It found that the sun's influence is not indefinite in its current form. It found that interstellar space is not a conceptual void, but a measurable environment. And perhaps most importantly, Voyager found that human technology can reach that edge and remain functional long enough to report back. This is what makes Voyager the first chapter in a larger story of signals, observations, and mysteries. Voyager shows what happens when a message is sent outward. It also sets the stage for the next question. If humans can send a message into the dark, what messages does the dark send back? In the next episode, the focus will shift from spacecraft traveling outward to signals arriving inward. Some of those signals will be short, some will be repeating, some will be famous for being unexplained, some will be understood but still astonishing. And throughout that exploration, the tone will remain calm, because the universe does not need drama to be strange. For now, Voyager continues. It is still traveling outward. It is still moving through interstellar space. It is still sending faint data when power allows and instruments remain. One day, Voyager's transmissions will stop, not because it reached an ending in a narrative sense, but because its power will no longer support communication. After that, the spacecraft will still exist. It will continue moving through the galaxy, silent and unobserved, carrying its record and its hardware into deep time. That final silence is not a failure. It is the natural conclusion of a mission built on decay and distance. In this episode, Voyager is presented not as a dramatic warning or a mythic traveler, but as what it truly is, a human-built instrument that crossed a boundary and measured what it could. It is a message in motion, and in the quiet between the stars, even a faint message can matter, because it proves that the boundary was reachable. The heliopause was not only a concept, it was a place. And Voyager went there. In the next episode, the perspective will reverse. Instead of following a message outward, attention will turn to the signals that come toward Earth from deep space. Signals that are not designed to be understood, but that still carry structure and sometimes surprise. In this episode, the solar system's edge becomes real. In the next, the galaxy's voice becomes audible. The message has been sent. Now it is time to listen.